I'm the Tutor Wizard. This is Willa, and this is Jasper. I know your name. And they're harassing me behind the scenes, so as usual, we'll put them in there. They're much cuter than I am. Let's do some math. I'm the Tutor Wizard. Please subscribe right here, and you'll get notifications for all the other videos in this series and many more. I'll just write it. This will be episode 2 in the series of trying to mathematically model the coronavirus 2. This is going to be Baby Bear Model 2. Okay, I know you were rolling in the dirt outside too. Basically what we're going to do is we're going to step it up. In the first video we just looked at one compartment in the infected individuals and we tried to analyze what was going to happen there. What we're going to do is step up one more to Baby Bear 2, and then we'll start doing Mama Bear problems in the next ones. Video 3 will be Mama Bear 1, where we start doing SIR or SIS. I haven't decided yet, but they're going to get more and more complicated as we go. So what does Baby Bear 2 do? It'll stay Baby Bear because the scenario is okay, but essentially what we're going to do is instead of just focusing on the compartmental model I, we're going to also focus on S, susceptible individuals, and now the infected individuals. So, and then we're going to try and see how they interact with each other. Again, what is this? This is the susceptibles, and this is the infectious individuals of the population. What we're going to assume is the total population is S plus I, which is fixed. What that means is N is a real number. The population isn't changing over time, but S of T and I of T are going to change over time, but they're going to be equal to N. They sum to N every time the total population of the individuals. Once we do that, before we start, what we're going to do is we're going to do the same thing we did in the last one. I'm going to build this transfer diagram or compartmental diagram. Then we're going to put a bunch of arrows in there. In this case, a bunch means we're just going to do one arrow to simplify. We've got rid of the birth rates and the death rates and all those kind of things. It's Baby Bear, remember, this is why we're doing it. We're going to analyze what happens when we just have two compartments and one arrow leading from susceptibles leading into the infectious. What we're going to do is we're going to call that beta SI. This is called classically bilinear incidence. This is what almost all models use. Any other video you watched on YouTube, they're doing versions of this too, beta SI. Let's do in this model, this is why it's Baby Bear 2. I'm essentially going to do the same thing I did in the first model, and what I'm going to do in every model, I'm going to derive a compartmental model. I'm going to derive the differential equations from that. I'm going to solve the ODEs. Eventually when they get harder, we can't explicitly solve the ODEs. In the Papa Bear ones, no. But in the Baby Bear and Mama Bear ones, usually yes, we can actually, this is why they're simpler, we can actually explicitly find the ODEs, solve those ODEs, and then depending on the scenarios, look at when we have equilibria or steady state solutions to these scenarios, and then look at the R0 and the general reproduction number on trying to find when the tipping point of when we'll have disease-free equilibria or equilibrium or an endemic equilibrium where this stays in the population. Before we do that though, this time what we're going to do is I'm going to explain this in much more detail, because this also, you're like, well, all of a sudden if you're trying to understand science, and I claim that I'm going to try and as mathematically or unmathematically as possible try to explain what we're doing with the mathematics in modeling these scenarios, where do we actually get this, and what is beta, and what are you talking about when we say this? First of all, let's look at what that means. This beta SI is the incidence term of a susceptible and an infected interacting with each other. We're trying to say how often we're going to get a new infected individual from the susceptibles. Let's break that down a little bit. First of all, to get a new infected individual, what we have to have is we have to have a susceptible individual and an infected individual meet and interact somehow, making the susceptible infected from that SI interaction. First of all, what do we mean by an interaction? First of all, the interaction could be between anyone. I have a population N of people. Some of them are susceptible at the beginning. Most of them are susceptible. A couple of them are infected. Once we do that, we start stirring the pot and we say, what's going to happen with that scenario? An interaction can happen between two susceptibles or two infected or an infected and a susceptible. So also we're looking at this and we're trying to say statistically, in these interactions, anyone can interact in that pot, whether you're two susceptibles, two infected, or a susceptible and infected. In that probabilities, though, I could have interactions like this: SS, II, SI, or IS, the 4 choices. And this is where the 2 is going to come from. When I multiply by 2, you're going to be like, where's the 2? You'll see, because there's 2 choices here, so the probability is double this. I don't know whether the first one was susceptible or the second was infected, or the first one is infected and susceptible when I pick pairs at random. Now what we're saying is we have a pot of n people, and I have a bunch of people in there, and they're interacting. Some of these are S's, some of them are I's. Every time they interact, what we're trying to describe with that is, in those interactions in N, we don't know what's happening, but they're all interacting with each other. So you can have two susceptibles interact with each other, two infected interact with each other, or this one or this one. This is where we're going to get new infected. So they're saying we're going to scrap those ones, those interactions we don't care about. So in the model, that's part of in the beta that we're going to do, we're going to have to encapsulate that scenario. We don't care about those ones. These are the ones that are going to give us new infections. But first of all, what they're saying is we need a contact rate for everybody in there. I'm going to call alpha the average interaction rate. Why is that? Because on average, what we're saying is, what is an interaction? We're actually viewing it statistically. We're saying we have a random jar of people, and we're going to randomly select two of them to interact with each other. You guys interact. That's not really happening, but that's what we're sort of modeling and saying what's going to be happening with an interaction. We know people are actually walking around in space and doing those types of things, but to model it first, this is what we're calling an interaction. This is where they get this bilinear incidence form. So one, I need the average interaction rate of alpha for any interaction of any two individuals in there, whether they're S's or I's or S and I mixed, because we need to know how are people contacting each other. So that's got to be involved in the equation of the beta of the contact for new infected. The second thing I need now is, in that, this alpha is just giving the average interaction for all of these guys, all of these scenarios. And I don't want that. We know that the infected aren't coming from this whole scenario. It's only coming from half of the scenario, roughly. So it's these ones that we want. So out of that, what are we going to have to actually get a new infected? I keep pointing here, it's gone now, I erased it. What do we need for the new infected? Well, I would need the probability that we get an S and an I in the interaction. I get one S and I get one I. And then the third thing I need is, just because I have COVID-19, I don't have COVID-19, and I should have used someone else. Just because the cameraman has COVID-19 and I don't, and we interact with each other, neither of us has COVID lockdown. Just because we interact and one of us has the infection or coronavirus doesn't mean we have to give it to each other. We need the non-zero contact rate for which we will actually get a new infection is what we need. 3, I'm going to say, let C, we're going to call it, for contact, I'm pretty sure is what they did. I'm stealing this from everybody else. But in the literature, we're going to call it C, which is the fraction or proportion of these interactions, of 2's interactions. If I get this, what's the proportion of these interactions which actually lead to a new infected case? So the fraction of SI interactions leading to a new infection. So this is what scientists are mapping out to try and say what the bilinear incidence of having this. Yes, we have to make mathematical assumptions about the homogeneous mixture, or like we're stirring a chemical or we're stirring iced tea into water to make a jug of iced tea. We're saying that the water molecules and the sugar molecules, roughly speaking, when we start stirring, have equal probability of interacting with each other, and this is mass action, and it will become a bilinear incident, and you're like, these are big words and fancy machinery that I'm using. Essentially what they're saying is this: in the total population N, I have a bunch of people, some of them are susceptible, some of them are infected. You can have interactions between anyone in here and we don't know who it is. So you can have SS interactions, infected interactions, or these ones are the ones which are going to produce new infections. But in that scenario, first we need to know what's the average contact rate in a population. This. And then we're going to map the crap out of this in a second. Then, what's the probability that we get in this scenario interactions? That I don't want all the interactions. I just want to know what's the probability of getting this type of interaction. And then in that scenario, not every one of these gives us just because they touch. Well, if it was like super corona and then, everybody that touched anybody and it just spread airborne, then it's going to be almost all of these C would be 1, just to guarantee. But if it's less than 1, what we're going to say is not every interaction gives us an infection. This combined gives us the beta that they're talking about. Let's see what these 3 are mathematically. This is the only one that we have to really change a little bit. To recap, in this interaction scenario, and this is what's going to happen in all the other models, because in all the other models what we're going to do is that we're going to start adding more compartments, which is going to make everything more complicated, more types of people that might be happening in the process. And we're also going to start adding more arrows in and out of the boxes, which will create more complexity in the model systems. But every time we do this, whether I'm doing S and I and R, and this will be the S and the I and the R, and you can have an A, and then you can have an SEIR, and you can, it doesn't matter. In this type of complication, what we're saying there is this will make the models more and more complicated. But in the scenario of where we have S to I or S to E in the other cases, the incidence rate is always going to be beta SI. That's always going to appear in all of the further models. Anything you watched on YouTube, yeah, they're using beta SI. What's beta? How are they building this? This is what this is going to explain now. In all the models, it's going to be that. One, all I need for this one is that multiplication of the alpha, the average contact rate of anyone in the population. Here, we have to do a little bit of statistics. First of all, we're going to assume the total population is larger than 10,000 in a population of about 8 billion. Good. I'm pretty sure. Yes, true. Why? Because in statistics, actually, when we're doing this with picking people, what we're going to do in interaction is basically we're just randomly picking two people out of that and say interact. That's what an interaction is. Out of that, when I remove one, the probability to pick an S in the interaction is going to be S over N. And then I'm going to multiply that by I over N, the minus 1. Because when I remove one of the S's, I don't have a population N anymore. I have a population N minus 1 to choose the I from. But we want it to be fancy in our formula to be a nice term where I want to replace N with N minus 1. As long as N is larger than 10,000, the error in replacing N minus 1 with N is less than 0.01% error in replacing this. Statistically, we want to make sure I can do this. Let me recap that one more time. In this one, this is the only extra math calculation I have to do, which is statistical. The probability of picking a susceptible on its own is S over N. The probability of picking, after I do that, the probability of picking I is N minus 1, but we're going to say it's approximately equal to N. And then what's the probability that you get this SI interaction? It's 2 times this, they say. And you're like, well, where did the 2 come from? Because I don't know whether the first person I pick is an S and the second person is an I, or the first person I pick is an I or an S. So there's 2 scenarios in there where I could lead to this. So it's 2 times this. It doesn't matter. It's going to become beta when we put it all together. And what do I need here? All I need here is the constant contact rate, or the constant fraction of these types of interactions that will actually lead to a new infected person. Now what that says is this. Recapping that, now I have a mathematical expression for all of these 3 processes. What this gives us is now we can say with some level of confidence, other than the fact that we've assumed that the population mixes like stirring iced tea, which it doesn't, we're aware. Give me a better model. Public health. Give me a better model. What that now says for us is the average number of new infected individuals over a predetermined unit of time is now going to be equal to, in that contact rate over time, the average contact rate in the population N. But I don't want all of those guys. I only want the ones which are SI interactions. So that has to be multiplied by the probability that in this interaction, the one that we get is an SI interaction. And then not all of those lead to, just because they interact, it doesn't mean you get a new infection. So there has to be some non-zero, but probably less than 1 fraction C, which this interaction actually leads to a new infection. And that gives me a mathematical description of the average number of new infected over a unit time is going to be what? Alpha times this probability, which was 2 times S over N times I over N times C, which I can write as 2 alpha C over N squared times S times I. N was a constant number, remember, he's a fixed population, it's never going to change. This is a number which they're going to call beta. The average contact rate of new infected individuals over unit time, beta SI. This is the incidence term. Okay, now we're going to start where YouTube starts. Beta SI. Who the heck is beta? Yeah, the first 10 minutes was beta. Now what we're going to do with that, we're not going to change the complexity of the compartmental model at all. We're not even going to put extra errors in there. That is going to be the next video because it's going to get a little bit more realistic. Actually, the next one's probably not. It's just going to be SIS, and then we may not put them. But now what's going to happen from this one, from this Baby Bear 2? Baby Bear 1 just has this, and then we had a couple arrows trying to just model and focus on him. But that says that it's either going to exponentially grow or exponentially decay over time, and that seems unrealistic. You can't just unboundedly grow or decay over time, and therefore we're going to change the model to Baby Bear 2. Once we do that, we start focusing on 2 compartments of the total population, N, which is now not going to change. We're saying it's fixed and it's constant, which also you would change in the more complicated models where N will grow and we'll put a constant birth rate or some influx of new individuals. We're going to do all those in the later videos. Right now, we're just going to stick to 2 compartments and 1 arrow between them. And now we've derived systematically what roughly we think this mass action bilinear incidence term is for the interactions of SI to produce new infected individuals over unit time. Having this, there's a couple clever things I'm going to do. So now I'm going to do the same thing I did in the first one and what we did in the actual, that big coronavirus one that I did for the first video. Now step 1 is draw your compartmental diagram or your transfer diagram. Check, done. All the work was just finding out what this term is going to be, and the arrow is going to go this way. Susceptible lead into the infectious. 2, derive ODEs from this. This step will be easy in the Baby Bear 2. This is why we want this, because we want to get an idea of how to mathematically phrase and structure these things and then analyze what's happening to the functions or the solutions we get from this. Again, also, if you've not seen this, so quickly let me do it from here. Now I have 2, so there's going to be 2 equations in this. It's going to be a linear, non-linear system of equations of ODEs. What that tells me is the rate of change over time of the susceptible population, which is the first derivative with respect to time of S, is going to equal negative leading out, negative beta SI. And the infected individual's rate of change is going to be positive beta SI. Already intuitively what we can see from this is if beta is a positive number, which we know it is, beta is a positive number, everything in the derivation that we used was a positive constant. C was positive, alpha was positive fractions of interaction rates, and then N is a positive population. This whole constant beta is a positive number. What that says is, whatever that rate of change is, if S now is the population, and this is positive, that says S is greater than or equal to 0, and I is greater than or equal to 0 for each of these cases, so they're both growing. What is that even saying intuitively as I look at this right now, before we even start? I'm going to hope that it says that the rate of change of the I's is just going to grow and grow and grow in proportion to this, and this one is going to decrease, decrease, decrease to where this one reaches the maximum capacity if there's no susceptibles left and all the infected dominate, and the total population will stay the same constant all the way through that scenario. That's exactly what is going to happen, but even as I look at that, that's what we're trying to say in setting up the compartments. We're saying if you had susceptibles and you just did this and there was no other leading in or out arrows, it's going to say that this is going to get drained and this is going to get pooled. I have sink and I have a source in graph theory. This is a connected network, directed network, and it's going this way, so everyone's going to pool into this category is what we're hoping it says. Mathematically, that is what it's going to say. From here now, what do we cleverly do? Well, we're going to do a couple of clever things. What we're first going to do is we're also going to say that this is our ODEs. We're now going to focus on this one again and solve that one. You can analyze the susceptibles when we get the bigger ones. This one starts out like this, and then you get the bumpy one, and then you're going to get 3 curves in there. What are they talking about? Well, this is the one I'm looking at, the I curve. So in there, we want to look at this one eventually. That's not what ours is going to look like this time. This will be in the more realistic mama bear, papa bear type scenarios when we do these. For now, what I want to do is, classically what we're going to do is focus on the infected individuals because we want to mitigate them. So in this model, it tells us something about both of these guys, but we're going to focus on what it says about these guys. I of 0 is going to be I naught, which is some positive number. I have to have at least 1 infected individual. Otherwise, there's no disease. So that's a positive number, and that's our starting point. This is our initial condition. Also, because of that, and I'm calling it I naught, the number of people when infected when I start, what would I call the number of susceptible individuals? S naught. So notice that because N is constant and it never changes, regardless of the time, S is a function of T and I is a function of T that's going to change over time. That's what we're saying. but they all stay constant in the carrying capacity. You can't, if there's 10 people and 9 are susceptible and 1 is infected, it's going to say all 10 will be infected eventually. That's exactly what we're trying to say, and that's what's going to happen. N, which is the constant number, is going to be S naught plus I naught. The original, that's still going to be the constant N. And over time, it's still going to be constant N at equilibrium. What that tells me is I'm cleverly prepping. It says that S is actually N minus I for all times, in particular, even at the initial conditions too. What is that? How does that help me? I can put that in there, and then we get a logistic equation. And this is what happens in ecology models and epidemiology. You're going to get a logarithmic equation is what they're going to call it, because you get an implicit solution which has a natural logarithm. That's why they call it logarithmic. Let's see what happens. From this, cleverly, we're going to focus on this ODE and then explicitly solve it in this case because it's baby bear 2. So we can substitute that in there. That gives us this ODE, which they call logistic. Why? Because it's going to have a logarithm and it's an implicit solution. This says this is beta times now N minus I times I. And so this is nonlinear. This is a quadratic in I. So this is a nonlinear ODE. Luckily, it's still separable. So even though we don't have a general technique of solving nonlinear ODEs, which is going to happen when we get more and more complicated systems in these series, we won't explicitly be able to solve for them. And this is why all the YouTube ones do the SIR models, but they don't have too complicated so they can actually still explicitly solve for the solutions and then draw the curve for you. Or they're going to use Runge-Kutta approximation to find approximate analytic solutions to these ODEs, which are nonlinear. It's hard to solve these things in general. What I notice is cleverly, this is separable. So let's do that. Let's solve this ODE. Step 3, solve and give me the explicit solution for this ODE, which they also skip. At the end, they're going to say this. Here's what the other YouTube ones are doing. They're going to say, and from this, we get I is equal to N times e to the beta t over e to the beta t times I naught over S naught. Good. Yeah. How did they do that? This is how. Solving this explicitly, I see it's separable, so I do this, I separate them. This is di over n minus I times I equals beta dt. I integrate both sides. Integrating both sides gives me, this one is not so bad, this one is partial fraction decomposition, so we're going to have to deal with that one. This one immediately gives me beta t plus c. From the other one, what I have to do is, now let's focus on this. The integral of 1 over I times n minus I di is a proper rational function, and it is factored, so I make a partial fraction decomposition guess. What I guess is that 1 over I n minus I is equal to a over I plus b over n minus I. If you don't know what I'm doing, skip ahead a minute or two and you'll see that we have the explicit ODE solved. Basically what YouTube is doing, skipping all the steps, and they're saying this is the explicit solution we get from that. It takes a few steps. This is the 4th try that I've been doing with this. So it was a -1, whatever. From this, I make a guess. Now I have to solve this. What I'm saying is I need a common denominator. This is the common denominator. What's this one missing? This one. What's this one missing? This. So dirty trick. My favorite dirty trick is a over I. I multiply by n minus I over n minus I plus b over n minus I. This one was missing I, so I multiply by I over I. From that scenario now, basically cross multiply and simplify this. What does that give me? This, which basically says what? I now have the left-hand side equals the right-hand side, and I'm claiming this is true right now. First of all, what you can do is you can ignore the denominator and focus on the numerator. If these two polynomials now are equal to each other, it says that the I coefficient and the I to the 0 coefficient have to be the same. This tells me negative a plus b equals 0, and NA equals 1. From the first equation, this says A equals B. And from the second equation, this says A equals 1 over n. So they're both equal to 1 over n. What does that give me? Now that I've solved for that, I know what the A and B are. From that, what I'm going to do is now I can explicitly solve the integral. This gives me the integral of 1 over I n minus I di is now equal to 1 over n. That was the a times the integral of 1 over I di plus 1 over n, the integral of n minus I di equals 1 over n, the integral of 1 over I di plus 1 over n. Now I'm going to take a negative out of this, which will give me negative the integral of 1 over I minus n di. Why did I make that move? Because I don't want to do this negative in the substitution rule. That's the whole point of why I want it, but now it's there. Now that gives me 1 over n times, I can factor the 1 over n out. This gives me this one is the natural log of the absolute value of I minus the natural log of the absolute value of I minus n. What does that give me? Now that was the left-hand side, and the right-hand side was the baby integral of dt, which we can now set equal to each other. This one equals the right-hand side. Let's move that up. This is the implicit form of this logarithm logistic. Now what do I want to do? I want to solve for I, essentially in this. What that's going to give me, first of all, I need to get rid of the log. How am I going to do that? Get rid of the n. So multiply both sides by n. That gives me the natural log of the absolute value of I minus the natural log of the absolute value of I minus n equals n beta t plus n times c, which we call that one a tilde. We're just going to call this one c again. Now what do I want to do? Cleverly, using log laws, subtraction on the outside becomes division on the inside of the logarithm. So I'm going to write this as the natural log of I over I minus n equals n beta t plus c. Now I can exponentiate both sides and get rid of the logarithm. And that will give me I over n equals e to the n beta t times, using the power or the exponent laws, times e to the c. One more time, I'm just going to let e to the c equal a. So this simplifies, and I have to find out what that a is based on my initial conditions. Let's do that. In this form, before I explain, this is an implicit form of the solution I dependent on t. Before I do that, I'm actually going to find the a first, and then we'll solve explicitly for this. At my initial conditions, when t is 0, I is I naught. So I put that in here. At the initial conditions, I naught over I naught minus n is equal to a times e to the n beta times 0. E to the 0 is 1, so that says a equals I naught over I naught minus n. And then let's be clever, and negatives didn't bother me the whole day, so let's try it one more time. We are going to take a negative out of this cleverly. This is two negatives. Negative, negative is I naught, so it does have a negative in both. I take it out. That gives me negative I naught over n minus I naught. Why did I do that? S naught. This is negative I naught over S naught. That's the A coefficient. What does that tell me? Here now I get I minus n is equal to negative I naught over S naught e to the n beta t. Now what I have to do, I have to explicitly solve for I. So we're going to do a couple of clever tricks, but what I need to do is have I on one side by itself and solve for I. So first what I'm going to do is bring this one up, factor something out, and get this. Should I do this again and hurt my brain? I'm going to get rid of this negative by pushing it to this side. I minus n minus I equals I naught over S naught e to the n beta t. All I did was get rid of that negative for myself. Why? Because I want to do this now. I is equal to I naught over S naught e to the n beta t times this guy, n minus I. This is I'm going to distribute this in carefully and then move it to the other side all in one step. That gives me I times 1 plus I times I naught over S naught e to the n beta t. And then that equals this, which is equal to n I naught over S naught e to the n beta t. Factor the I out of this, and I get that I of t is equal to n I naught over S naught e to the n beta t over 1 plus I naught over S naught e to the n beta t. That's not quite as fancy as I want it, so let's clean that up a little bit more. How can I do that? What I see from this original expression, I move it up here now and I've prepped it. I separated this out a little bit. I have this and I have that. If I had that in this term, I could cancel them off cleverly, which is what I'm going to do. How do I factor that out? Well, I need I naught over S naught. Well, you can't just do that. That changes it. So I'm going to multiply by S naught over I naught also. And now multiply by 1 twice. And then now I can factor I naught and S naught out of that. And that will give me I naught over S naught n e to the n beta t over I naught over S naught e to the n beta t plus S naught over I naught. Cancel, cancel. And this now finally, dot, dot, dot on YouTube. The explicit solution for that now of the logistic equation is equal to I equals n e to the n beta t over e to the n beta t plus S naught over I naught. That is the explicit solution to the logistic equation. That took me like 4 tries. We had to stop the camera several times. I counted a negative wrong. Yeah, YouTube, maybe fill in the gaps of dot, 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 dot. There's the explicit solution. Now I'm not even done with that. This is predicting the behavior of our infected individuals over time now. What is it going to tell us? There's one more clever form. They put it all on the internet also. They read it like this. If I cleverly, again, dirty trick, what if I multiply by e to the negative n beta t over e to the negative n beta t? How they pose this on the internet is this. They say I of t dot 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 is equal to this now. N over 1 plus S naught over I naught e to the negative n beta t. That's how they write it. Clearly, what am I going to do with that? I'm going to show you sort of what that gives us and how do I know and what does this picture look like so I can tell what's happening to the infected. That's what you want. Like, that's all I wanted from the whole talk. Show me the graph. I put the details in too. You can fast forward. From this, now you're talking about f and g again. Yeah, that's right. Let f of t equal nt over t plus b, or we know what b is now. S naught over I naught. Let g of t equal e to the n beta t. This gives me, if I, let's compose some functions. I don't want to, yeah, now it's extremely important. We'll get the solution to this system. What is f following g of t? This is f of g of t, which is f of e to the n beta t. Now I put that wherever t is in this expression, which gives me n e to the n beta t over e to the n beta t plus S naught over I naught, which is our explicit solution. Our solution is the composition of the monode function, they call it, and the exponential function. This is what the explicit solution is to the logistic equation. Now let's see what that gives us in analysis of what our system looks like. The other videos say there, here's the equation we derived from the compartmental model. And then they say dot, 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 the explicit solution I of t is clearly n e to the n beta t over e to the n beta t plus S naught over I naught, clearly. And moreover, they go one over and do it again, and then they say, okay, this is what it looks like. Here's the carrying capacity n, and it says it's going to look like this. It's going to get awfully close to that as time goes on. What is that saying? And what are they doing here? Why does this look like this? It's the composition of those two functions. However, if you look at our preliminary videos, I give you an explicit, detailed way of using calculus in the first and second derivative to find it's monotonically increasing as this first derivative is always positive. It has one inflection point at log of 9, which has a value of 5, is where it switches from concave up to concave down. And then you can explicitly draw the graph of this function using the calculus of variations. If you've taken calculus 114 or something like this, this is what we expect you to do at the end, sketch curves. let's do a baby example, and then we'll finish off this baby bear model 2 with some specific details and sketch one of these guys. Okay, let's use this as in general, this is what they say, but nobody likes all these letters in here, and so we're going to get them back out of there. How do I do that? What I'm going to do is suppose that my total population in a baby model with the baby bear scenario, that's okay. We're going to assume we have 10 people. Out of those 10 people, 9 of them are susceptible, and 1 of them, our initial conditions is a 1. So I of 0 is I naught, which is 1. What that tells me is, and what I'm going to also do is I'm going to assume beta is equal to 1/10 for convenience. Remember, beta is the approximate rate of new infections over a unit time. This is 1/10, about 10%. What does that give me now? That will give me an explicit something I could sketch and plot points and draw. That says I of t is now what? N is 10. 10 over 10 is 1. So I'm going to just get e to the t over e to the t plus s naught over I naught is 9 over 1, which is 9. Now we have closer to calculus. If I change that to an x, I say f of x equals 10 e to the x over e to the x plus 9. What does that look like? Sketch that. Systematically take the first and second derivative and sketch what this happens. Watch the other videos and you can see this. For now, what we're going to do is I of 0. It says it in the model, and I claim that I now solved this ODE. Remember what this is saying is, in the ODE, we had di dt equals beta n minus I, and we're looking for the function that does this and has that the initial condition is 1, and I claim it's this guy. Is it? What's I of 0? 10 e to the 0. E to the 0 plus 9, which is 10 over 1 plus 9, which is 10 over 10, which is 1, which is the initial population of what I started with. So yes, check, he is the guy that's doing this. And graphically, what is that telling me? Oh, we're going to have to try again. What does that tell me? I need to draw a bigger picture. This will be our carrying capacity of all the individuals. 10 at 5, 1, 2, 3, 4, 5. I cheated. Watch the other video. I systematically sketch these and show you how to use calculus. 1, 2.1 is log 9. And then our initial, what it's saying is this curve represents the infected individuals, but now it's a function of a single variable t. So we can plot it. Time axis, I of t. What does this look like, they say? And they're like, oh, clearly it looks like this. So what we found out was we have an inflection point on the curve at log 9 and 5, turns out, for this function. Then we find out it's monotonically increasing its concave up between here and concave down between this interval. So I get something that looks like this. And this is what they say it's going to look like, this curve. This is I of t for this one specifically with these numbers. What that now tells me is what's going to happen with this. Do you see, even in calculus, the limit as t approaches negative infinity, we can't do this. It makes no sense. But if you go to the other end, the limit as t approaches positive infinity of this, what do we get? It's this guy, 10 e to the t over e to the t plus 9. How do I take this? Now I use the dirty trick, e to the negative t over e to the negative t, which is the limit as t approaches infinity of 10 over 1 plus e to the negative t. This goes to 0. And so I squish that in there, but you get 10 over 1, which is 10. The limit at infinity is, it says it has a horizontal asymptote of 10, the carrying capacity. So what that's going to say is, regardless, if I have a box where I just have S's, which are the source, and a sink, which are the I's, and they're moving in there, over time, eventually at some time, you're going to reach the carrying capacity and there will be no susceptibles left, and the infectious will just dominate this. And this is what the curve is saying, and this is what its shape is telling us. It starts off with an initial population of infected individuals of 1. And that if you let this progress, there is no way to stop it. It will eventually grow, not quite exponentially, but in a monode exponential version of, or a logistic growth to the carrying capacity. let's do one more little thing. Why didn't we have to talk about the general reproduction number or the equilibrium in this case? Because in this simple model, there's no other choice. You can't have a tipping point or anything you could do with the parameters to stop this scenario. Everybody's just going to funnel into there. Everybody will become in the category of infected in this baby bear model. Also why in the next video that we do, we're going to make it more complicated, because this can't be clearly what's happening, because we have common colds and stuff like that, and it doesn't just dominate and everybody gets it and then it goes away. It clearly has to have these two, so we're going to have to start adding other arrows into the compartments to see what's happening, and then we get more complicated models. But every time we do that, this one is always going to be beta Si. This is the most common one we use. So in the last step, let's look at what we got with this. But this analysis systematically does the same thing as when I normally find equilibria and the R naught. In the other videos, we have to do that. Here, it just says clearly, look, you're going to start off with all susceptibles and maybe a couple of these infected, but over time, eventually, you're just going to get growth to it being all infected individuals in that population. So there's one more. If I was going to look at this, or basically what we just did systematically told us what was going to happen anyways, but if I wanted to look at the equilibrium scenarios in this case, it should tell me the exact same thing. So if I wanted to know when di dt, which was beta n minus I times I, when does that equal 0? And then remember, we put the stars because we're at equilibrium. When is this 0? Well, this is a quadratic and it's factored, so yay. This says this is 0 if and only if I star is 0, or I star is equal to n. And that's exactly what the analysis of the graph just told us. At equilibrium, when eventually there's no more change in the system, everybody became infected, and it's the entire population, which was constant. And there's none of this. Why can't I have this? This scenario can't even happen. Why? If I think about it again and I look at the graph, and this is why the picture's worth 1,000 words, and I do the mathematical analysis of this, starting at a positive value, I naught, which was 1 even in the baby one we just did, and it's monotonically increasing function, that says in this model, if that I of t is the function that we got that solves that model, which it does, we're starting at a positive value and only increasing ever. So we can't go back down to 0. It could never reach an equilibrium of no infected in this scenario, in this model, because it's starting at a positive value and increasing always. Where is it increasing? To the carrying capacity. The only other equilibrium is n, the total population. This disease, and in this model, if that's really what's happening, the disease will not stop until everybody in the entire population has it. Russell Peters has a similar thing to this too. Eventually, you'll all be beige eventually. You'll all be beige eventually. Subscribe here. We're going to do a whole bunch more videos on this. The models are going to get more and more complicated, and in about 3 or 4 more videos, we're going to have a reasonably accurate model to what YouTube is already force feeding down your throat, and then skipping all the steps. I'll see you next time. A plus B equals 0, which means they'll be negative to each other. Finally. Math is hard. I've tried this 3 times and I got the negative wrong somewhere, and I tried to take it out and then it didn't work. Math is hard. I tried it 3 times. The negative is going to get you. It'll get me. It still gets me. Math is hard. I hate negatives.